All right, so again, we're assuming we have an aggregate demand function. All right, it looks like this. So the more money, so if here are prices, so if there's more money relative to prices, then people are going to demand more stuff. Sort of makes sense, doesn't it? So how are we going to justify it? Well, either you can have money in the utility function, so people care about money. You could have cash in advance, so you need money in order to buy stuff, so people accumulate money. You need something in additional to what we had above, but we're just going to posit that for now. All right, so prices are flexible, the money's neutral, right? The government prints a bunch of money. Well, money is just the unit of account for prices, so all the prices adjust up, and nothing really changes in the model. Okay, so how does that work? Again, prices adjust to the money. You double the money, you double the prices. Okay. So you need something else. In this model, we're going to have a nominal rigidity, which we're going to call a menu cost. So what does that mean in practice? It means that prices and wages are fixed at some time period 0. All right. Once they're, and then the economy, there's an outcome of the economy. So time 0, the firms have an expectation over the money supply. All right. They choose their prices, and then boom, at time 1, when production actually happens, the money supply might turn out to be different than what they expected. And if so, we're going to call that a money shock. The firms want to adjust their prices, but there's a cost. They have to actually pay a real cost Z in order to change the price. Okay? So if these menu costs are large relative to the change in the money supply, then firms are not going to pay the price because it's not worth it for them. They'd rather just get the less optimal production instead of paying this expensive cost of reprinting their menus. So in that case, money will not be neutral. The actual demand will change. The real demand will change. All right, so let's do this the proper way. Okay, so when do firms want to and not want to change prices? So when do firms do not want to change prices? When do firms not want to change prices? Assume that each producer anticipates that the others do not change their prices. All right. Ask whether, given the menu cost, given that nobody else is changing their price, do I want to change my price? If the answer is yes, then that's not an equilibrium. If the answer is no, then, oh, excuse me. I read this the wrong way. Given the menu cost, do they find it worthwhile not to change their own price if they don't want to change their price? This is kind of written in a confusing way, isn't it? I should say, ask whether, given the menu cost, firms don't want to change their price. Let's rewrite this a little bit. I'll rewrite in the slides too. Given the menu cost, do firms want to change? Maybe we'll say, do they find it worthwhile? Let's do it this way. To change their own price? If no, then not changing the price is the best response given others' actions. That's better English. We'll call it a symmetric Nash equilibrium, right? Nobody else changed their price. I also don't want to change my price. Then nobody wants to change their prices. Nobody wants to deviate from not changing your price. All right, so how are we going to find if that sort of equilibrium exists? Well, we're going to compute basically two things for an individual firm. We're going to say, what's your profit if you adjust, if you do change your prices, given that no one changes their prices except for you, and compare it to the profit if you just leave your prices be, if you don't change them. If that difference is less than Z, then the firms are not going to want to change their price. And then this Nash equilibrium exists. So we have a calculation. Our calculation is going to look like this. So here is our labor market equilibrium. It says that the wages have to equal the demand to the power gamma minus 1. Okay. How do we get there? Well, real wages are equal to labor. Labor is equal to demand, and demand is equal to M divided by P. All right. So let's scroll down here and look at the firm's problem again. Okay, so this is just the same as what we had in the slides a couple slides ago. All we're doing here is we're going to put this y inside of this expression, right? We're going to take this y, the demand, put it here, and then eliminate one of these negative ones here. So we're just bringing the y into the parentheses here. Okay. And then rewriting a little bit, let's now take this pi. You can see that we're taking pi to the power negative n, putting it inside. Okay. And then over here, we're doing the same thing. Here's our pi divided by p to the negative n, and we're now replacing y by m divided by p. Okay. So if the firm doesn't change its price, if it just goes with the prevailing demand without adjusting its prices, then we're going to have this result, and the firm's profit is going to be as given here, which is basically just MP divided by P. Why is that? Because PI divided by P is still 1, right? The firm is, as I read it right here, since none of the firms changed the prices, including this particular firm, PI will be equal to P, and we're going to get MP minus MP to the power gamma as the profit of the firm. Okay, so far so good. Now, suppose that the firm is going to change its price, okay, assuming the other ones don't change its price. Just like before, it's going to set its price so that, I mean, this is just the markup equation, right? PI is equal to the markup times the wage. Okay, that doesn't change. And we're dividing here by P, the price level. Okay. Sorry about that. Anyway, right. So this is just coming from the firm's optimization problem as before, and then here we're making a substitution. We're substituting in m divided by p to the power gamma minus 1 because we got this actually from the last slide here. So we get here that in the labor market equilibrium, the real wages are just equal to the demand to the power gamma minus 1, m divided by p to the power gamma minus 1. Make that substitution. This is now the firm's optimal price. Okay. Let me actually just flip back one slide. Yeah. Never mind. Okay, that's the firm's optimal price. Now let's substitute that into the profit function. Okay, so you remember the profit function just says, it's the same as in this last slide, in fact. So here we have, just check out this equation here. We're just recopying that down here below. Okay, that's the same as this one, except for now we're gonna substitute out this optimizing price. Okay, so we're doing that here. So let's see here. Right, so it's this expression to the power 1 minus eta. So that's where we get this from. It's just multiplying, or taking this to the power 1 minus eta, that's what's here, times mp from here. And the same thing there, to the power negative eta. Doing a little simplifying. Here you can see this stays the same. Here we're multiplying, we're putting in the mp into here, so that's why we get a 1. Minus, and then here we're putting this mp in here, we're getting a gamma there, okay? Slightly simplifying. Now let's copy that expression. Okay, here we get a gamma plus eta minus eta times gamma, and here we get an eta plus, gamma plus eta minus gamma times eta. Oh, it's actually the same thing. Why do we get that? Let's take a look here. All right, so negative 1 times 1 is negative 1. That's going to cancel with this thing. Then we're going to get 1 gamma. We're going to get 1 positive eta. And then we're going to get a positive gamma times eta. Okay. Why do I say negative gamma times eta? No, we get a negative gamma times eta, right? Negative gamma times, or gamma times negative eta. It gives us a negative gamma times eta. And then here, gamma, positive eta, and a negative gamma times eta, so it's actually the same. Alrighty. Let's see here. So let's just take this eta over eta minus 1 out. So we get, we're separating this power. So we get a negative eta there. So we've got two terms that are identical. Okay. Then we're going to take this term out because we have the same term on both sides here. So we're going to get an eta divided by eta minus 1 times eta divided by eta minus 1 to the power negative eta, and then this term. Okay. Now finally, we can do this little trick. This is hardly a trick at this point. This is just basic algebra. But you can see we're going to get 1 divided by eta minus 1 times this term. Okay, so, that was a lot of algebra to get this profit, optimizing profit if the firm adjusts and no one else adjusts.